Hi everyone. Thank you for joining me with this session, this 3 hours deep dive. I won't keep it that long, but honestly, I haven't timed myself, so I hope you will bear with me. So write you an actor system for great good with JBang, JDK 19, records, pattern matching, virtual threads, a bunch of nice stuff, cool stuff. So this originally was a deep dive that was meant for 2 people. One of them could not come, so it's 3 hours only with me. And I think I don't want to brag, but I deserve an applause for, just for encouragement. Thank you, you're great, You can leave. It's all I wanted for today. No, just kidding, just joking. Okay, so let's start. And by the way, this is the other person, Andrea Peruffo. We did this deep dive, but in another form. It was a workshop, 2-hour workshop, and it went kind of short with it. And so here we were at JBCN conference, and in fact, we are having paella, as you can see. And I don't know if anybody heard about this book, Learn Your Haskell for Great Good. So, yeah, not many. I don't know if you're interested in Haskell. It's actually kind of dated book at this point, but you can see the title rhymes. This is no clone of this title, and because I thought it sounded nice. And so if you're interested in that kind of thing, it's a bit dated now, but it's a funny, whimsical book to learn more about Haskell. And anyway, the talk is about actors. Or is it? So, yeah, this is not literally a talk about actor systems. I mean, it is not, yeah, I can see your surprise. It is not only a talk about actor systems. In fact, we're going to talk about actor systems, we're going to compare with actor runtimes, but it's also meant to explore features of the recent version of the JDK. And in fact, it was born as a series of blog posts that you can find still on my blog. And on my blog, you can find these 3 blog posts that were actually written for JDK 17. So if when you're home, when you're bored, you can still take a look at those. And the cool thing about JDK 17, it's an LTS release. So those version of the examples that we're going to see today, you can actually bring home, and if you can actually manage to use JDK 17, because it's an LTS, you can actually use it right now. While JDK 19, it's not an LTS, but... Okay, a couple of words about me in particular. My name is Edoardo Vacchi. This is my handle pretty much most places on the internet. Before what I'm doing now, I've been doing research about programming languages, domain-specific languages, compilers, interpreters at the University of Milan. And then I joined UniCredit Bank in the research and development group. And finally, now I am at Red Hat, where I do mostly 2 projects, or 3, depending on how you count. Drools, the rules engine, and Cogito, which is kind of the cloud version of all of our engines. Okay, so because we have a lot of time, first of all, I should slow down because they told me that I go very fast usually, but usually I have only 50 minutes slot. I can tell you the reason why we came up with this talk, the ideas behind it. And so I wanted to show you this 20 lines of code that we're not gonna go through line by line as we will for the Java code. Because it was the thing that inspired me to write this blog post and prepare this deep dive. So it's about 20 lines of Scala code, a bit terse. Most of them are one-liners. But it gives you a full implementation of a working actor runtime with very little. I mean, it's just using a bunch of features from the JDK and then some putting them together, and it works. And it's kind of inspiring, Actor systems, I don't know if you've ever used one of them, but they can feel like something complicated or magical, but really the ideas behind them are not that many. And I mean, learning about those can help you a lot in thinking about your problem and how you can solve them. So writing one can be a learning experience that will bring you some ideas that you can actually bring home to things that you're doing, possibly. So how many of you are familiar with actor systems? And it's not just a few, it's a few people, not bad. So this snippet of code, it's dated 2012, so it's about 10 years ago. And 10 years ago in Scala, you could write this snippet of code. It was pretty functional, and you can functionalize it. It was working, and you could have this interesting tiny bit of code that implemented a fully working actor system. So in a way, you may wonder if this talk could be rephrased or titled, "Has Java reached feature parity with 10 years old Scala?" But, you know, this is kind of a troll question. Well, I do like Scala. I'm not like a fanboy. I've been writing some Scala, especially while I was at UniCredit. And actually, I wrote actor systems using akka. This is the code that we will actually be writing. And we will go one line by line and understand every single line that's happening here. Yeah, this is really just trolling because, you know, there are different languages, there are different constraints. Java has a different pace in the way it can acquire features over the years. We must be very conservative because of the constraints with backwards compatibility. But in the last few years, we've seen a lot of new interesting features. And so this is tongue-in-cheek, but actually that's what I was actually thinking when I thought about this talk. So can I actually get to the level of terseness of this snippet of code just using Java features that we have more or less today? And at the time, it was Java 17. So what you will bring home is, well, you will learn about new Java 19 features, but really is Java since 8. So it's a few versions. You will learn an interesting concurrency model if you never have heard of used actor systems. And the other thing, you will learn about JBang. I don't know how many of you actually know or have used JBang. How many? So it's just a bunch of people. It's an interesting platform. I don't know how to call it, but it's a way to write your scripts using pure Java code, so not a different language. It's just in a way, it's a launcher for Java code. That allows you to script your programs and use Java just like if it were a scripting language. So we will be able to write like pages of code and just running right away without you know, launching an entire IDE. So we'll see how that works. And of course, you will learn how to write concise Java programs using some tricks that will make people hate you. So that's the best part of me. So. Yeah, because the idea was that I really wanted to do some sort of code golfing with it. So I played with Java syntax and the Java features so that I could get it smaller enough, but not in a way that it's unreadable. So it should be easy to understand still. Okay. So here's an agenda. We're going to do a couple of pauses, a couple of breaks. So you can have coffee, like 10 minutes each. And this first part, I'm going to blubber for almost an hour, so it's the right time. If you didn't have coffee, it was the best time to have coffee. But yeah, I will try to keep it fun, and then we will see. I mean, I haven't timed me really. As I said, I usually go very fast. This time I'll go, you know, I'll take my time. And of course, after the break, we will actually start doing the actual coding, but we will see some code even here. So it's not like we're going to see just, you know, blah, blah. And so in the second part, we're actually going to write the actors. And then the actual runtime, because especially if you're not familiar with how actors work, you're not familiar with how you would write the code for an actor, it's really interesting and useful to first try to run one. And so we will write some actors against the runtime that we have already prepared at home, you know, like baking programs in TV. We already prepared this at home. And then we will actually write the actual runtime. And then we will also rewrite, or at least modify, the same actual runtime that the first version will be untyped in a typed version, which is interesting. And then we'll take another break because we will definitely be tired. At least I will definitely be. And then we will go to the last part. So this part, we usually share all of this talk, but the last part in particular is the part where Andrea is the best. So I'll try to make him justice and make it as good as he does usually. Yeah, we will see something about Loom. And so first, we will write a chat using still our actor system, the typed version. I won't go exactly through all of the details of it because it will take a lot of time, but I will show you, the main things. And then we will introduce virtual threads and Project Loom and see how this actually changes the way you can think of your code and you can write of your code and even question, in a way, the content, the entire content of the talk, if you will. Okay, so let's start. So we'll start with the definitions for actors. What is an actor? So this is lifted basically, literally from Wikipedia. So an actor is a computational entity that in response to a message, so it's something that receives messages, can concurrently do any of these. So it could do all of them, it could do none of them, or a combination. So the actors can send a finite number of messages to other actors, can create new actors, and they can designate the behavior that should be used for the next message it will receive. So I receive a message and I decide what I should do next. Well, we'll see what that means in a bit. And in a way, everything is meant to be an actor. So in an actor runtime, in an actor program, in an actor system, you're meant to basically use actors everywhere because that's the best way for things to interact. So why actors are useful? They're useful for modeling stateful systems because an actor can contain state. I would even say it should contain state. So it encapsulates states in a way that it's thread safe. So you can do parallelism, concurrency. You can do distributed systems. Not with the actor system that will write, but the idea with actor system is that you can have multiple deployments of this actor system and they can communicate kind of transparently between each other because the way you interact with these actors is not dependent on the fact that they're local or remote. So that's a way they're particularly used for communication systems, for networking, you name it, or IoT, for instance. And yeah, it's a concurrency model. It's relatively simple. And the interesting thing, it allows you to adopt a single thread kind of reasoning to your program. You can think of the body of your actor as if it was executed in one thread at a time, which is kind of the core idea and what makes it so simple and so easy to use in a way. And then it's message-based, so there's this concept of a mailbox that we will see. Okay. So as for the implementation, you can think of an actor as the combination of these three things, a function, something, a method, a function, something, a procedure, something that models the behavior of the actor. Then we have some state, because as I said, actors are meant to include some state. And then you have a message queue that we call the mailbox of the actor. Okay, so I don't know, a function plus state, does this ring a bell to anybody? What's a function plus state? Does it have a name? Interesting answer, an object. Or, we'll see. Okay, so that's a good answer, but there are other answers. Okay, we'll see that. So you can think of an actor like this, unity, this thing that has a behavior, which is our function, I mentioned before, and then some state, which is private to the actor. So kind of like an object, right? You have the object, you have the state, the fields, the properties, whatever you call it, and the behavior, which is usually methods, right? And then you have this mailbox. The mailbox is a queue, usually, the message comes from outside, it gets put inside the mailbox, and because it's a queue, then some message at some point will be taken out of the queue, will be dispatched to the behavior will read the contents of this envelope somehow, and do something in response. For instance, in this case, it puts it in the outbox, so to speak, of the actor, so the next iteration, or at some point in the future, will be actually delivered to another actor. So all of these things are meant to be asynchronous in that you cannot really know beforehand when they will actually happen. You don't even need to know. You shouldn't know. Okay? Okay, so that's the basic idea. All right. All right, so someone said objects, so the actors kind of like sound like object. Functions, actually, functions plus state kind of sound like objects, which is a good answer, but again, there's another answer. No, yeah. Huh? What? Sorry? An agent. Oh, that's kind of, fancy, but no, I was thinking something much more. I was thinking about the closure. Well, we'll get there. Okay, so messages versus method. Since we mentioned objects, you could think of methods and say, so what's the difference between a message and a method in a way, right? Because the actors receive a message and then do something. In particular, there are some programming languages, Smalltalk, for instance, where methods are actually called messages. So, well, it is weird, right, in a way. So you send a message to an actor, but you invoke a method on an object. But Smalltalk is an object-oriented programming language. It was the father, or at least one of the fathers of object-oriented programming. And so why do they call them messages? In fact, some people think that actors are proper OOP as envisioned by Alan Kay. And by the way, that in the picture is Alan Kay, and that's the picture that is on Wikipedia. So it was pretty cool that there was a picture on Wikipedia of Alan Kay that is scratching his chin just like my Shakespeare here. So this is Joe Armstrong, who unfortunately is no longer with us, but he was contributor to the Word of Actor Systems, creator, I think, of the Erlang programming language. And in a bunch of tweets that were shared with me, he is commenting about this. So he said, you should have lots of little objects. So when you model a system, any kind of system, you should have lots of little objects with private memory that send messages to each other. As Alan Kay said, the big idea is messaging. Some languages do this, but Java and C++ do not. But then they are not proper O language. Again, I guess you may have heard of this debate, what's proper object orientation, but sometimes there's even the debate, what's proper functional programming language. They're kind of fuzzy definitions, so yeah. Anyway, the interesting thing about this thread is that there was another reply by Joe Armstrong says that Smalltalk messages are actually synchronous calls. So even though the idea was that you could send a message to other objects, in fact, in Smalltalk, these are implemented like method calls for, I guess, for optimization reasons. I don't know. But there are languages where this concept is actually really core to the model of the language itself. So there are Erlang, of course. There are Elixir that can be seen as it's a different language, but runs on top of the same VM as Erlang. And then Pony, which, if you haven't ever heard of, it's an interesting programming language that puts together not just actor system and, actor systems, but also typing which is not part of Erlang and Elixir. We will see that in a bit. Interesting. So a couple of examples, since we have talked a lot about what actors are meant to be, how actors are implemented, but why should I use those? Where are they useful? So this is an example of, you remember, I don't know if you remember the 3 items that I listed before. I forget about them usually. So an actor may send messages when it receives messages, may decide of its next behavior for the next message it will receive, and then it can spawn other actors to do something. So a good example of this is a server system, that's handling HTTP requests. So upon receiving an HTTP request, what we could do could actually handling it directly. So we block, we do something, and then we return. Or we do that asynchronously, but we handle it and we do not reply to the client until there's an actual result. So that's a way to do it. Another way to do it is to return immediately with an identifier, for instance, and then the user, the function, the rest endpoint, the rest call terminates immediately. The user has got this identifier, and then with this identifier, they could either poll or they could, I don't know, subscribe to some WebSocket. So what happens is that the computation that should be handled is too long to be answered directly. And instead of blocking, we wanted to do it asynchronously, to do it in the background. So in order to release, in order to be able to serve other requests, we spawn a task of some sort that finishes computing that particular request. So that the response. And so I called it the Computation Watchdog. So this could be modeled with actors. So every time I get a request, I create an actor to handle that request, and then I do my business, and then when I'm done, I send another message and say, I'm done, and we go on from that. So that's one reason why I would spawn actors. Another thing that I mentioned, I mentioned sending messages, but that's pretty self-explanatory. But what about behaviors? So I mentioned that an actor may designate the behavior for the next message it receives. So that's a way to model state machines, finite state machines. So a classic example of a finite state machine is the vending machine. So let's suppose we have this vending machine that does initial state. This initial state, the machine is just waiting for something to happen. And let's say that first you insert the coin, and then you get to choose what you want the machine to release, like to give you back. Let's suppose that every item costs the same. So first you start in the initial state, then you start inserting one coin, and so we transition to the next state. And the next state, let's call it wait coin. And it waits for coins, so there's a loop here. It stays there with the next coin until, and see the other branch, the other arrow, you see that the other transition as a guard, it says, yes, I'll get another coin, but I will transition to a different state when the total amount of the coins that I've received is at least 100. So basically what I'm saying here is that when you insert an amount of 100 through coins, then you can transition to the next state where you can pick one of the items that you're interested, that you want to get, like chocolate or Coke or something. And so once you have reached 100 or at least 100, you get to the vent state, and now you wait for the choice, you release the item, and then you get back to an initial state. So that's a simple state machine. So all of this can be modeled using actors with a different behavior. So kind of like the actors receive the first message and changes its own behavior so that it will be able to receive different types of messages and respond to those messages in a different way. Okay? So that's the idea. Okay, so we're gonna implement that. We're gonna see that in an actual implementation. So actor runtimes. Okay, so The first snippet of code was about 2012. Let's go back in time, a little bit of history. What was the world like when Java 8 was released? Before Java 8, well, we had Java 6, we had Java 7. We didn't have lambdas. Java 8 was kind of a revolution in the Java world for that one, at least for that feature. But before that, one of the few languages that allowed you to write, first of all, typed code, and code that was functional in a way, use lambdas. Well, functional, again, it's a fuzzy concept, but it allowed you to write lambdas in a syntactically pleasant way with Scala. And at the time, the languages that were statically typed were mostly, the mainstream programming languages were mostly, I would say, Java, C++, C#, before Java 8, so JDK 5, 6, 7. So I would say that's one of the reasons why a lot of people flocked to other programming languages where typing was not that heavy, was not that verbose. So they flocked to languages that were dynamic, like Python, Ruby, or on the JDK, on the proper JDK, Groovy. And yeah, typing in those languages were lightweight because there was no static typing. It was all dynamic. And definitely was lighter weight, but you had other kind of issues. When Scala was introduced, I think it was kind of a revolution because it did have static typing, but it showed to the mainstream, when it entered the mainstream, to JDK developers, that you could have your cake and eat it too. You could have a language that felt kind of like a dynamic language, but it could be written in a very concise way, which was kind of powerful at the time. And another thing that I think is not highlighted as much is that there was an actor library as part of the standard library of the Scala programming language, which I think contributed to its success because it showed you how you could write concurrent programs in a very simple way without using threads, without using just features. And I think features were introduced, well, completable features were introduced with Java 8, so we only had those features that, Okay. So now I'm going to show you a few snippets of code using a bunch of languages. I'll start with Scala because, again, it's the source of inspiration. I'm not going to use the original library. I'm going to use this library. Well, it's a very famous library and framework that's called Akka. And the first example, this is basically the hello word for actor systems, is the ping pong. So the ping pong is you have one actor, you have another actor, and they send a message to each other. The first sends ping, the other responds with a pong. And when the first receives a pong, it responds with a ping, and back and forth, like a ping, you know, ping. Yeah. So, and that's what it does, you know. I don't want to really go through a lot of this, but what it does here, you can see there's a state in this class, and it's a private state, and it's mutable. And you can see that it counts to 0, and when it counts to 0, when it goes to 0, it stops doing the ping pong. Until it is not 0, while it's greater than 0, it responds to the sender with a message. And I don't want to go really through this, but that's all it does. So one thing that I want you to focus on, though, is the syntax here, and the reason why I was inspired to write this talk using recent features. So what you're seeing here, it's a function that takes any and returns unit. I don't know if you're familiar with the Scala syntax, and if you are, I'm gonna do one trick that it's not. I'm going to rewrite this in a way that's not equivalent, but it should help understanding. So what I'm writing here, so first of all, yeah, that's correct. So receive is a method that takes a message of any type, which means object, And unit is just a synonym for void. So this is a method that returns nothing and consume an object of any type. So that's not really well typed. I mean, it takes any object. That's not nice, you know. Yeah, it could be. It's error prone. Why did a language like Scala, that was so focused on strong typing, went this way? And that's kind of the answer I want to give you, but by going through history. So, apart from the syntax, apart from the signature of this method, I want to take a look here at what's happening here. So the third syntax that you're seeing here can be rewritten like this. So you see that our message is disappearing. So I'm just making it more explicit here. So the object message is matched against the case ping. So it's checking whether it's of type ping and then doing something with it. Keep in mind what's happening here. So, and now I want to show you what would happen with Java. Now, keep in mind the framework, keep in mind the time. The Akka framework was born especially with Scala end users in mind. So it was very convenient for Scala users to write it like this. It was very concise. But Java users were left with this, which is not as nice. So as you can see, we can literally see that there's a void return type. There's an object here. So it's what we just said. It's not that nice. And then we had to do an instance of and check whether it was ping type, and then cast, and then do our business. So at the time, it was not that nice to write actor code this way, but you could. Not that great, you could. Now, the question is why is Scala so weird about actor systems? Why is Akka that way? Why was Akka that way? Because nowadays we have a different API, and I wouldn't make it do it justice if I didn't say it. There's a typed API nowadays. But anyway, Scala was kind of, I put this kind of a diagram here, but it's, there's no measures. It's a quality kind of idea. So Scala is at the extreme, if you will, of the type programming languages that we could run on the JVM, really, because Groovy, Ruby, and Python, Groovy definitely, but Ruby and Python had JVM implementation as well. And those Groovy, Ruby, and Python were more on the extreme side of dynamic typing. Nowadays, no longer like that, because we are adding more and more features on top of the language to allow them to have type checking, compile time type checking. But at the time, that was kind of the idea. And notice that I'm saying dynamic typing and not weakly typing. I'm saying static typing, not strong typing, because Python, for instance, is definitely a strongly typed programming language. It's just that it throws errors at runtime when you try to do type conversion that are not allowed. So why would Scala be a statically typed programming language that would use that signature object? Well, the roots are in the language from which the idea was borrowed, which are Erlang and Elixir. Again, I don't want to go through the syntax of these languages. I don't want you to learn Erlang or Elixir. But what's really happening here is that we're doing some pattern matching against the message. These languages are dynamically typed. They're strongly typed, but they're not statically typed. So the message that arrives here could be any kind of object. And all I can do is check against its structure and make sure that it's a tuple that has the shape that I expect. So weirdly enough, Erlang use small letters to indicate atoms, which are called symbols in other languages, or you can think of them as intern strings. So it's just, you can think of it as a string, if you will. And these are variables. So it's checking whether it's a ping, and then it's doing something with the values inside these tuples that are not the first item. In the Elixir syntax, it's very similar, and you can see that the syntax here is different, more familiar. It looks kind of like Ruby. It receives a message, and with the message that it receives, again, it checks whether it's a tuple of 3, and the first item checks the type, basically, that's written like a symbol. It says, is it a type? Is it typed as a ping? Is this message a tree tuple, and is the first item a ping? If it's a ping, then I can look inside and check whether it has a count of some sort and do my business. So that's where the inspiration comes from, and that's why the signature for an ACA program originally was like that. Why it's object? Because it takes inspiration from these languages where typing was dynamic, and because that's also some discussion that we could have. Some may argue that it's easier to scale system in this case because you can roll out changes in a distributed fashion. But that's for another day. Now, yeah. So that's why Erlang and Elixir I would put on this end of the diagram. So now this is a long introduction just to say, can we improve over this? Can we make it easier? Can we make it easier to understand? Can we make it easier, to write nicer in general? In Scala, we had the match statement that kind of make the idiomatic to pattern match against an object to verify its type. But in Java, we only had instance of, which makes it really, really non-idiomatic, really ugly. It's actually something that we should not do. People would say, you should use the visitor pattern, which would make this even uglier, in my opinion. So the tools of the trade. What we're going to actually use. So we're finally here after the long introduction. What are the things that I'm going to use? Okay, so it's where we start with the tricks to make your colleagues angry. Okay, so this is your regular static void main, right? Your regular hello world program. The one difference that with a regular hello world is that I put hello world inside a constant. And you can run this. I mean, we can actually run this. So I can actually make sure that everything works. So here, and let's just say hello. Yeah, I think you can see how this would work. Yeah, I can make it slightly more concise. And then run it through JBang. Actually, this is so. Oh, what's that? Yeah. Problem with my setup, so I shouldn't have done this. All right. There we go. And this should work. So this is so trivial that actually I don't even need JBang. I can actually run it through Java because I don't know if you are aware, but the Java runtime launcher for Java programs, I don't remember ever since which version, maybe already 9, maybe 10. It's able to run short program snippets, one page, one file code snippets directly without any intermediate step, without any special runtime. So you can actually run this hello world exactly without any external tool, and that's what I wanted to show you. So the first thing that you'll notice here is that this is not public. That's the one thing. So we can actually get rid of that. Then I'm gonna say instead of a class, I could write interface, which should give you shivers already. I think. Why? Well, because I don't know if you know it, but interfaces can hold a static void main method. And if I use interface, then I can drop. The defaults are flipped. So you know that Java has some people would say weird defaults. I don't know if I will call them weird, but they're defaults that have a history, let's say. And in the interface, these defaults are actually flipped. So all fields are always public, static, and final in an interface. And all methods are always public. This you should know. But you could also make static methods inside. So I can just write static and have my hello world with a lot less keywords. Then I can also import static from system, and then instead of system.out.println, I can write out.println. This is lesser known, but you may know already. So I can reduce my class, public class, to this beauty. So nice. Oh, it's it's still another word. Notice this. This is not really making it short, but it just looks nicer to me. Instead of the string array, I can use string var args because it's still an array in bytecode representation. So it just looks nicer to me. Yeah. So yeah, and it's a way to rewrite my code. And I'm going to use these tricks, basically, to write the actual system later so that it looks nicer and it's a bit shorter and it stays in one page. So these are the tricks that will make your coworkers angry. Interestingly enough, while I was preparing these slides, there was this article by Brian Getz on simplifying the onboarding on the JDK, making it hello world for first newcomers, simpler to write, easier, shorter. And the idea was going from this, again, to instead this. So that's pretty cool, right? You can drop the class container, you can drop a lot of the modifiers, and you can even drop the argument if you don't really need it. So, and then if there's a static import that we can do to make the println shorter, you can really have, you can finally code golf with your friends that you know, make fun of you because Java is so verbose. Right? But, you know, with the interface, we can get pretty close already. Yeah, that's nice. So, yeah, people say, is this code golfing? Actually, the code golfing reference is also a reference to that article in that Brian Goetz is saying going shorter than this is just code golfing. I mean, it doesn't even make sense. I mean, we could get to a point where you just write the statement, but what's the point? Okay, so let's see more code golfing. So more tricks, more features actually of the JDK that we're going to use to make our program shorter and shorter while not losing a lot we're not losing anything, I would say, in readability. So these are our classes. Of course, I guess people here are familiar with records, and we're going to shorten them using records. But let's start from our receive method. You see, it's very ugly. This is a different example, right? Let me just explain what I'm doing here. Let's suppose that we have an authorization kind of API. So you have either you can send the auth message with a login and a token, authorization token, like a no-auth token, I don't know. And then you can also do guest login. So with the guest login, you will have to just send an email, like you did with FTPs, you know, anonymous FTPs. So you have two cases now. So you have either you can receive a message. So this is old ACA style. You could receive a message which will be an instance of auth, or a message which is an instance of a none. And if it is an instance of that message, then of that type of message, then you would cast and then you would do your business, which is, again, kind of verbose and also a bit ugly, right? First of all, we can simplify this using a recent feature that's called pattern matching in, for instance of, which actually, let me show it again. Neat, huh? So, instead of having to do the cast within the body, basically you can do it within the expression. Or to be more precise, what you're saying here is that you're checking the type of the message reference, making sure its type is auth, and if the type is auth, then you are making available within the body of the if a new binding, new variable that's called a, which is of type auth. So basically, it's kind of doing this all at once. And the same for the one down, you see, for a none. So this is the enhanced instance of with pattern matching. Of course, these are our classes, and you will already know that we can rewrite them much more concisely using records. So all of that boilerplate goes away because I can use one record and write all of that code in 2 lines, which is pretty neat, of course. Or now, the cool thing about this is that you can still use this syntax here, but with records, you also have deconstruction patterns. So, or as some people would call them, maybe it's proper pattern matching. You can actually match not just against the type, but against the structure of these records. And you can bind variables to the fields that are within these records. So instead of doing auth and assigning to auth to the A variable, I'm deconstructing the record and binding the fields in the order they appear to 2 variables, login and token. You can see that at the top I'm using var, and at the bottom I'm using the explicit type. These are both legal. If you want, you can be explicit. If you don't want, you can be implicit. And the cool thing is that this reduces a little bit the noise in your code, because instead of going a.login, a.token, you can do login and token. This is simple. This is not maybe worth the time for this example, but as you have a bigger structure, nested trees of objects, this could become very convenient. And notice that I'm not showing this here, but you can actually nest pattern matching. So you can do auth of, I don't know, name, or of address of, I don't know, and nest records and deconstruct all of them. More code golfing. Oh yeah. So we've been using ifs with instance of, which works, but it's still kind of ugly. And we have the new switch expressions, the enhanced switch actually, because it's both an expression and a statement depending on how you use it. And yeah, you see, this is combining both pattern matching and a switch. So what I'm doing here is I'm switching over message, and I'm switching over the type of message and checking if it's the type auth, and then deconstructing it, getting the variables out, doing the same for an on, and then I have a default case to handle in case it doesn't match with none of them. So that's already compacting a little bit my code, and it's getting closer and closer to the Scala code. So this is the improved switch. These are records that we saw. These are deconstruction patterns. These are var patterns. And then I can do something extra. I'm probably repeating this if you guys were in this room this morning, but maybe some of you weren't. So I can also declare an interface, and an interface with this special keyword, sealed interface. So sealed interface is a special kind of interface. Well, actually, sealed is a special kind of keyword. It could be an interface, it could be an abstract class. What you're saying when you're sealing is that your subclasses are only a fixed number and only a fixed list. You can enumerate the types, or if you define them all in the same file, you can also be implicit like I did. So your auth is now implementing login info, and a known is implementing login info. Because they're defined in the same file, this means that only those types, only those subtypes are allowed for login info. Why is this convenient? Well, this is convenient because now, let's suppose that I can write on receive using, instead of object, login info. If I am able to write it like this, then I can still switch, but then I can drop entirely the default case, because now I have a sealed type hierarchy and I have exhaustive pattern matching. So I am sure there are no longer any other cases that could match, because there are only 2 possible subtypes. And so I can entirely drop the default case. And the compiler will tell me if I'm making a mistake. If I add a default case, it will complain. If I'm not ending all of the cases, it will complain. If I'm adding only one and I'm not ending a default case, it will complain. I mean, it will cover all the cases. So that's pretty cool. So now we're getting really, really, really close to what we had in Scala, because it was pretty much the same. So, I mean, we're getting there, okay? And it's how this looks when you're using Akka and Java and pattern matching. You see? Not bad. It's pretty close. Okay, yeah, I wanted to, at the end of all this first section, I wanted to say that this is not necessarily the case for Java, not even for Java 8. When Java 8 was released some time after that, they released an API to create a sort of pattern matching using an embedded DSL. So using lambdas, basically you could do this pattern matching. But of course, it's a bit clumsy, a bit cumbersome, and of course, proper pattern matching in the language, it's much better, much nicer to look at. But right now, even if you're not using the latest JDK, you can actually use that, of course. But that's not our game. Okay, so the idea, yeah, is that we want to get there. Oh, yeah, and I wanted to show you because I wanted to be fair, is that while I was writing the blog post, some friend of mine, actually I think it was just really Andrea, just said, oh yeah, you're writing in Java. Victor already did. So the first snippet was written by Victor Klang, which was one of the original contributors, I think, to Akka. Also wrote the same snippet of code using Java. Damn it! I did it for nothing. But as you can see, the date here is still 2012. So it didn't leverage all of the features of the language that we have now, and it definitely wasn't written just exactly the same as it is as I wrote it. So still worth it. Okay, so this would be a good time to have a break. So in the next session, as I said, there will be live coding. So if you'd like, you can leave and take a coffee. We'll see you back, hopefully, in 10 minutes. The next section does not really require you to have any knowledge about the previous part. So if you have friends, please let them come. And hopefully, I'll see you back. See you. So I hope you had a good time with the first part, and if you didn't see the first part and you came for the second, wow, thank you. But if you enjoyed the first part, well, this is where I start to make mistakes. So I hope that was fun and you had a good memory of that part. Anyway, you will help me. So since a lot of you didn't know about JBang, of course, I'm going to say a couple of words about that. So JBang, it's a way for you to write scripts using Java, just Java. So this is the jbang.dev website. Basically, you can write scripts that you can literally run from your command line without having to without having any other thing on your machine besides the JDK and of course the JBang launcher, which is very simple to install, especially if you use SDK man. If you don't, I really suggest you to use it. It's a way to manage multiple versions of the JDK on your machine and multiple other SDKs and tools on your machine, and it's really useful. Yeah. Okay, so I think we can get started with the live coding. So in this live coding session, what's that? Sorry. What's that? Okay. So in this live coding session. Okay, it's locking up, just the demo effect. Okay, so in this live coding session, we're going to see the ping pong actor, definitely, the one that we can become friend already with during the first part. I will do an hello word, which is even simpler in order for us to get more accustomed to it. And yeah, and I'm using, as you can see, old style paper because my memory sucks, and so I will never remember this by heart. I also have snippets, but I don't remember the order I usually go through. So, okay. All right. So So as you saw, and in case you didn't believe me, you can see that I can literally embed my program inside an interface, and that will run. So as I said, I can actually use the Java launcher, and that will be pretty fast. But I can also use JBang, and that will work just as well, especially if I can type it correctly. There you go. You see that it works. Now, there are several reasons why I prefer to use JBang. One of them is that, for instance, I can use these special directives here to automatically define some of the behavior that I want for the program. For instance, I can configure my compiler and my runtime so that it automatically passes flags for enabling preview features, which otherwise I would have to remember to write on the command line, which I will definitely forget. Anyway, yeah, we are here with our hello world. And I can close this to have some more space now. Okay, so in all our discussion, we said that the actors have a behavior. I may have mentioned that an interesting feature of actors is that we interact with them, especially in the proper, fully functional distributed runtimes, in a location-transparent way. So we don't invoke directly methods on these objects, on these actors, but we send messages to them, and we send messages to them through an interface that sometimes it's called a reference, sometimes it's called an actor reference, and sometimes it's called an address. I'm going to call it an address. So I'm going to start by writing this address here. There you go. It's an interface. So as you can see, it's a pretty simple interface, and this is actually fancier than it needs to be, but it's convenient later. It can be just like this. So the one method that the address needs is tell, the public method. You're already noticing, I guess, that this is a public interface. It's obviously static because it doesn't really make sense to have a non-static interface. What would that even mean? And of course, I'm not saying that the method in the interface is public static void because it's public void because it's the default for interfaces. So it's an instance method and it's public, of course. So I can write it on one line. This is the one of the ways you can make your coworkers angry. And of course, your code formatter, which you will disable for this because otherwise, okay. So as you can see, it's really simple. It's just saying you can send a message to the objects, and send is a valid name. The traditional name is tell. You tell something to an actor. But I'm gonna write it like this because now, if I write it like this, I can chain several tells one after the other. It's just for convenience. So it's literally the same thing. You could just say semicolon, tell. But this way you can chain them. And that's it. OK, that's pretty simple. OK, now I blabbered a lot about the behavior actors. So what I'm going to say, what I'm going to write here is the behavior. So what's a behavior? So I have explained that behavior for an actor is the thing that it does when it receives a message, right? And in particular, what I said in the definition is that the actor may designate the next behavior for when it will receive the next message. So in a way, I could write it like this in a concise way. So a behavior could be defined as a function that takes a message, right? And then it returns the next state. So I could write it like this. Of course, the next state, it's called a behavior. So I could write it like this. I'm going to write it in a slightly different way. So behavior, it's probably a type. Message, we already decided that's an object. And we will see that we can change that later when we'll do the typed version. But for now, we're starting with the untyped version. So I'm going to write object here. So instead of using behavior, I'm going to use this. So yeah, OK, so I wrote this in a comment. We should be all familiar with Java, especially Java 8, I hope. So this is defined as what? Function, for instance. That's a good answer, yeah. So let's write it like this. Interface behavior. And then I'm going to extend function. And then that takes an object. And then returns something. We'll see what that something is. I'm going to call it effect. And then we will see what that is. Now, this is a good way to define it, but I'm going to, well, interface is nothing. It's interface, right? That's why I don't usually type everything out. And in fact, I have a different version here. That should work. There we go. Which is slightly different because I wanted to be explicit. Function is perfectly clear, it's perfectly valid, it's perfectly okay, and it is actually the one that you'll find on the blog. But for the sake of explanation, I wanted to be explicit here, and I'm going to use a proper interface, a proper single method interface. I can also annotate add functional interface, but then the line would become longer. So no. And it's just just a hint. It doesn't really not much. So it's equivalent. So what I'm going to do here is defining effect. So what I'm going to do here is defining effect, and my effect should be this one. Yes. My effect is defined this way. It's a transition between two behaviors. You see, it's taking a behavior. Of course, if you'd like, we can write it in a more mathematical way. So behavior returns another behavior. Okay, it's a transition between behaviors. So instead of just instead of being my behavior a function that takes an object and returns the next behavior, it's a function that takes an object and then returns a transition to the next behavior. Okay, so depending on the behavior, just a different way to encode it. Okay, so these are my building blocks. Now, the other thing that I'm gonna need to write a program is the actor system. So let's say, okay, yeah, let's say I'm writing it here. Okay. Yeah, no, let's write that later. Okay, so well, we will have this this actor.system interface, and we have this method actor_of, and we'll see how that that will work in a bit. So what I'm going to do here is writing an example, a very simple example, an example of an actor that receives a message and then stops receiving messages. I think after the effect, we should probably see, yeah, we should probably see some types of effects. Yeah, but we will see them as we try it. Okay, so let's try here our example. So let me enable some of these imports. Now, you see that, I'm going to need this one too. So you see that I have this directive here, sources actor.java. This is actually sourcing, this is actually saying to JBang that I'm going to need this actor that we had prepared already for you to save some time. But then we will actually prepare that. Okay, so this is our hello world, and it's the usual hello world. Now, what I'm going to do here is that we have imported. We don't really need these anymore because we're importing them. So I'm going to create my actor, and I'm going to create an actor.system, and this takes an executor service. So I guess you probably already familiar with this. I'm creating an executor with, for instance, a fixed thread pool. And this gives me an actor that I can now use. Okay. So as you remember, well, maybe you would like to know what the type of the actor is. And the type of the actor is address, I'm telling you. What is wrong here? Oh, no, I'm already making mistakes. Okay, so this is the actor system. Sorry. So this is I'm first creating the actor system, and this gives me back the actor system. And then the actor system will let me create actors. Okay, so this takes this function that I call constructor, and let's not spend too much time on what this takes. We're going to discuss this later. It takes a lambda that returns another lambda. The first argument of the lambda I'm calling self, and we'll see why in a bit. And then this is actually the behavior. You can see this from the hint here. It's taking a behavior. So the behavior that we're writing here will be the behavior that received one message. It prints out the message it received. Let's say printf. And we say received message. And that's it. And then the actor should return something. So if you recall, the behavior should return something which is an effect. Now, for now, I'm going to write actor return actor dot. I need actor. I can just say actor just dot stay. And yeah, that should be it. Okay. So basically what we're doing here is we're saying we're creating an actor. The actor has this behavior. The behavior of the actor is to receive messages and print the content of the message. So what I'm going to do here, I'm assigning the result of this actor of to a variable here. And then I'm going to say actor.tell. If you recall, this is an address. You will see this is an address. And the address takes... What is happening here? Okay. And I'm gonna send it some message. Okay. Okay, so let's see if this actually works. Yeah, you can see that at the very bottom we're reading received message hello. Not much. We can also try to send it several messages. And since these are chainable, I can also say .tell word. Interesting. Yeah, no, it's an awesome program. And you see, I forgot to add a new line, and it says hello, receive message word. So that's pretty much what we were expecting. Let me add a new line here so that it's nicer to read, but that's pretty much it. Okay. Now, yes, I have defined the effect. I have defined the behavior. Yeah, we should probably discuss a little bit about this stay. What is the stay? So stay, it's a predefined effect. I don't wanna always write these effects one by one. So I have defined some predefined effects that do something very simple. The effect stay, it's a function that takes its argument and returns the same. So we're going to see how this is used. But basically, this is saying, I don't want to really transition to another behavior. I want a loop. I want to, if you recall the vending machine example, let me go to the slides. If you recall the vending machine, this is a loop like this, okay? And that's it. So this is a very simple example of behavior. So I also want another behavior, a behavior that once you enter, you can never leave. So basically, it's a final state. I'm going to call this the die behavior, the die effect. Sorry. So the die effect is the effect it's an effect you enter and you can never leave, and it's modeled basically with another behavior that every time receives a message, just says I'm dropping the message. Now this die effect, which I'm gonna use, this die effect actually uses another function. This is a function. Yeah, I'm using a capital letter in a function. I'm naughty. So, and that's just because I wanted them to look the same because they're all effect, and also because, you know, I want to confuse coworkers. You know, you get the drill. Yeah, the way become is defined is really not that complicated. As you can see, it takes a behavior, which is your next expected behavior, and given the old behavior, it returns the next behavior. So it's a transition. So it really encodes it. It's a way for you to encode a transition. And so what I'm saying here is that the transition that I'm doing is to a behavior that I'm defining right here, that for all messages that we'll receive, will always say, I'm dropping this message. So I'm going to use these, and I don't really need to have them defined here because I'm porting them. So let me comment it out. And let's try that, will we? Okay. So yeah, no, it was already like that. So what I'm saying here is I'm receiving one message, and then the next message will be dropped. So let's run it. As you can see here, the first message was actually handled by my behavior, but the other message was dropped because it entered that state, the dead state, where the message where messages can no longer be handled. And that's useful because in a state machine, you may need to define a state where the actor is actually dead. It has to be collected. It has to be destroyed. So that's a way to model that. OK, so that's working. All right. We have enough items to go further with our example. So finally, we're going to write our ping-pong routine. So this is going to be a little more interesting, a little bit more fun. And we're going to start with this. OK, so as I said, we're going to need two actors, the ping receiver and the pong receiver. OK? So I'm going to duplicate this and write the pong receiver here. OK? Which at the beginning, it's exactly the same actor. Of course, it's not going to die immediately. Otherwise, it wouldn't be too fun. Yeah, let's start simple. Let's create two messages. And the way we're going to write these two messages is by using records. So I'm going to write a ping message, and I'm going to write a pong message. OK? So here's what's going to happen here. I don't know the message that's going to come, so I need to switch over the type of the message, right? So as you know, lambdas can be shortened if I use an expression. I don't need the brackets here in that case. So I can actually rewrite and make this compact almost as compact as the Scala version if I use a switch expression. So I don't really need I'm going to use a switch first of all, and I didn't say that. Of course, I could use if message instance of ping and then do something, but we're going to be fancy and use switch statements. And so I could write switch and message, and then in the case it's a ping, I'm going to do something like, I'm going to stay, for instance, in this state. And in the default case, I'm going to stay in that state. And of course, I'm going to have to return this. And this should work. But in case this is no longer a statement, no longer an expression, so I have to write it like this. And I'm missing a semicolon here. Yeah. But, so this should work. Doesn't do nothing interesting so far. This could work, but I can be fancier, and I can compact this as using a switch expression. So if you use a switch expression, I can actually write it like this. And I can drop this, and instead of returning stay, I can yield the stay, but because it's a one-liner, I can just do it like this. And I'm done. So this is the first very bare-bone version, which is not doing much. It receives a ping, and it stays there. So it's not going to show us anything, but it's a start. So I'm going to do the same here for the Pong. So let me duplicate this. So let's call it Pong receiver. And there we go. OK, of course, the Pong receiver is going to receive a Pong. Now, what we're going to do is that, of course, we have the ping. We have the ping receiver. We have the Pong receiver. They receive the right type of message, but we want them to communicate to each other, right? So what I want to really do here is basically, what I really want to do here is that when I receive a ping, then I want to tell the Pong receiver, so I'm going to write Pong receiver, tell, and then I'm going to say new Pong, and send the Pong, and then definitely I want to stay in this state. So what I need to do here, because this is an expression instead of return, this is the keyword that you use in switch expression to return from the expression. So you don't use return, you use yield because it's not a return from the function. So I'm going to yield stay. Okay? So this only partially compiles. It complains what it complains about. Pong receiver cannot be resolved, of course, because it's defined after that. So okay, let's move this below. And now I'm going to do the same for this guy here, right? And you see where I'm going, I guess. This is never going to work. Because now it's the ping, the problem, right? So yeah, no, this is not going to work. And if you have any ideas, you may have some suggestions. Maybe I could, I don't know. Do you have any suggestions? I could use the class, for instance. Send the sender in a message. You're disqualified because you probably knew the answer already. Yeah, that's the right answer, but it's too right. Yeah, that's correct. Yeah, so the wrong answer would have been, I could move these to fields, but that wouldn't have worked anyway because of the order they would be initialized. The compiler would complain anyway, so it doesn't work. And the correct answer is, let's use the address. So we have the address of the sender here, and we have the address of the sender here. So basically now, my messages contains an information about whoever sent them. So instead of saying ping receiver, now I'm going to say p.sender.tell, and then Pong, I'm going to say self. So that's why I needed self. And why I cannot use ping receiver, same reason, it's going to complain. So I need self. I literally need self. Of course, we have learned already that there's a fancier way to do this, which is deconstructing parents. So let's use that. Okay, sender. Okay, and same for Pong, right? So var sender, and then to the sender, I'm gonna send a Pong. Well, definitely, no, not really. I'm gonna send a ping, not a Pong. I cannot type. I'm not really good with computers, I'm sorry. So, okay. So that's what we're going to do, all right? So The ping receiver expects a ping. Then the ping, it's deconstructed. If I do receive a ping, I send the sender back a pong with my own address so that they can respond. Because when they will receive a pong, they will deconstruct, get the sender, which was me, and they will send to the sender, which was me, themselves. They will send the ping with themselves as the address. So we can try to run this, but of course it won't work. Why? Let's see. So if I run this, it won't do anything. Of course it won't do anything because I'm not sending anything to anybody. So that won't work by definition. So I'm going to kick this off by telling the ping receiver that I want to send them a ping with the address of the pong receiver. Okay? So what do you expect to see here? A ping pong. This is not going to work. Wrong click, forget that. And let's see. That is interesting. What? Good idea. Maybe I should print something. Otherwise, I have a very expensive hand warmer, you know. Anyway, it's a bit cold in here, so it's not that bad of an idea. Right, so I should definitely print ping, and then I should print pong. All right, so let's see what happens here if I do print something. Yeah, that's more like it, okay? All right, that actually works. So our example was a little bit more interesting because we had a counter, okay? So one way to write a counter would be, well, let's try. I mean, I could like write, let's say, counter here, okay? I want to count down to 0. So the idea here could be every time I receive a ping, I'm going to count down, okay? So is this going to work? Not really, because this is a lambda. So because it's a lambda, this is supposed to be final. And I can be implicit about it being final, but even if I'm implicit, yeah, this is a syntax error, but it's still going to complain. I cannot really modify that. So I'm going to be nasty here, and I'm going to use an atomic integer just because it's not really useful. It's bad. It is bad. The reason why this is bad is that I've been trying to tell you that the cool thing about actors is that they're thread safe. So I wouldn't need an atomic integer. That's useless. It's just an overhead. But I'm going to use it nonetheless just to show you the idea here. So the idea, of course, is that I'm going to count down. So I'm going to initialize to 10. And then every time I receive a countdown, a ping, I'm going to count down. So counter dot decrement get. Okay, and just decrement. Okay, and yeah. Okay, so this is not going to do anything for now because now I have to check the counter. Okay. So what I am going to do is use a special statement, a special clause in the case statement that allow me to check against the guard. I mean, actually, I can do this with an if, of course. I can do this. And, of course, if this is greater than 10, this is greater than 0, then I'm going to do this. Otherwise, I'm going to do something else. And, well, let's write it. Let's write it all. So if it's if it's not greater, if it's 0 or smaller than 0, I'm just gonna stop. So let's just write it like this. So this should work, except I need to yield a default. So that's why I wanted the else branch. So that's it. So this is actually going to work. Let's try it. Hopefully. Yeah, you see that it stopped. So after 10, it has stopped. Right, okay, so, okay, so I wanted to show you the feature with a when clause. So we can actually add guards. These are called guards. We can enhance our case with a Boolean expression, and so we can make this more compact, which is not necessarily a way to make our coworkers angry, because this is pretty readable. So in this case, it's fine. And in the case, now the other case that we have here is when we have received a ping, but we're outside the boundaries of the counter. So we're 0, right? So we can still deconstruct here and just stay. And in this case, this means that actually I can write in a more compact way using the implicit yield. So let's try this again. Yeah, as you can see, just the same behavior. Now, the thing is, this does work, but I'm using an atomic integer just because I just want a mutable reference. And the cool thing about actors is that really they are executed in a thread-safe manner. We'll see later why and how that works, but for now you have to take my word for true. So, okay, so let's rewrite this in a different way. So, okay, so what I'm going to do here, I am refactor this to a method. Yeah, and I'm going to call this ping behavior. Okay. So I don't want to use the atomic integer, atomic integer anymore. I actually want to use a proper counter, a proper integer, because as I said, I don't really need to be thread safe in that way. So this is my counter right here, and I can now write this this statement like this. It's much simpler. Of course, I'm not mutating it, and we'll see why in a second. This is not going to do much right now. Let's see just how it gets called. So the idea, I'm going to call it like this. Okay, I'm going to call it. Let's go maybe on a new line, so it's more readable. Okay, so I'm going to start the counter at 10. What's happening here in my behavior is that I now have a variable parameter of the method, which is a counter. And yeah, I'm checking the counter, but I'm never modifying it. So how do I modify this? This is a way to write mutable state in actors, which is kind of counterintuitive in a way. You have to get accustomed to it. It's an idiomatic way, especially in some languages. And this is the first I want to show you. So the first way, it's to become. So here's where become becomes actually useful. And behavior, the next behavior, is the behavior that you have when you receive a message, and you invoke yourself with an incoming message, and the counter is increased by 1. This is not exactly the same as the previous, but it's okay for now because I'm increasing the counter at another point, but it's for our intents and purposes, it's okay. So let's see what's happening here. So I'm designating the behavior at the beginning of my actor as a static method. So it's pretty much like the lambda that I did at the beginning, but it's just that explicit. I just wrote it as a proper Java method. Now, what I'm saying here is that when I handle a message, I'm going to invoke this method. And what is happening here is that I'm passing along the self address, the message that I have received, and at the beginning, the counter is 10. Now, the next time I receive a message, if the message is of the proper type and the guard is true, then I'm going to change my behavior. And the actual behavior is going to stay basically the same because I'm still receiving the same type of message, but I'm going to update the variable. So at some point, the counter will become nobody told me that it's wrong because it's -1. Come on, guys. You need more coffee. When it gets to 0, of course, it will stop doing this and will stay in the same behavior. So, let's see if it works. Yay! All right. Now I'm going to write this in another way, which should show even more that this is actually thread safe. So if you recall, and I think you should recall, the behavior is an interface, right? And of course you can implement this single method interface with Lambda, but you can also implement the behavior using a class because it's an interface. So let's do that. So what I'm going to do here is I'm creating a class within this interface, so it's still static, it's still public. So I'm going to call it ping behavior, but this time with a capital P because it's a class. I'm not that nasty. I'm going to implement the behavior, all right? And now this is complaining, of course, because it's saying, oh, what are you doing? You should implement the method. And the method is a receive method. Right, so what I'm going to do is copying this over because I'm going to do the same thing pretty much, right? And yeah, now of course it's complaining about a bunch of things that are undefined in this class. So what it is undefined? Well, first of all, the counter. So the counter, it's a variable, quick fix. What I'm going to do, it's creating a field and I'm going to call it counter. And it's a private int and it's mutable. All right. And what about self? Well, self is an address and it's the address of myself. So let's fix this and I'm going to create another field and this is going to be final. I can actually be shorter and let them be non-private, but yeah, let's do this. Okay. All right, so now, of course, this is final, so I need a proper constructor here. So let's create a constructor for it, okay? And of course, I don't really need this to be public. And there we go, all right? So this is starting to look kind of nice. As you can see, the receive method does not contain any weird stuff. It doesn't contain the address. It doesn't contain a counter because the counter is part of the class signature. And this is becoming something. This was becoming something for the sole reason that I wanted to update its state, which is weird. And so in this case, I no longer need to do this. And actually, what I can do, which is nicer, is that I can increase my counter, can increment this counter here. Decrement. You're paying more attention now. Okay, so this is now the body of my behavior, my actor, so to speak. And as you can see, it's pretty nice. I mean, it's simple. It mutates states, but in a safe way. We'll see why later. And yeah, it has a constructor. All we're missing now is actually creating it here. Now, if you recall at the beginning, this was called was called in the constructor. And the reason why I wanted to call, or the initializer would be called. The initializer, maybe it's a better term. But the reason why I wanted to call it a constructor at some point, it's because, well, it is the constructor. Wow. Okay, so this should be doing exactly the same thing as before. But we should initialize counter to 10. That's correct. Otherwise, it won't do anything. Thank you. I don't know why I'm counting down. It's so easier to count to 10. I just wanted to make things more complicated for myself. Okay, there we go, right? Same behavior, same thing. But written in 3 different ways. Well, 2 different, yeah, 3 different ways. Okay, so we are... Yeah, we can spare still some minutes. Okay, so I'm going to show you very quickly the vending machine because you can find it online, and especially I don't want to bore you too much. You get the idea about the behavior and how to become something. But really, in this ping pong example, really you didn't see why you would transition to another state. The state we were transitioning before was just for the sake of updating a variable, which I think in this case makes more sense to writing like this. Oh, by the way, you recall that actors were a method, a function plus state, and it asked of you, what's that? So is it a function? Is it a closure? Is it a class? So keep this in mind. We'll get back to that. Okay, so we wanted to show you the vending machine. So let's switch very quickly to the slides. So recall, there's 3 states basically in this example. We have the initial state, we have the wait coin state, and then the vend state. And then once you reach the vend state, you can only receive the choice and then get back to initial. I just want to show you how you could model this using our actors. So I have 2 records because we only have 2 types of messages, coin and choice. Let's switch back to the picture. There's coin, which makes me transition from initial and then stay in wait coin state. And then once I reach 100, I transition to the vend state. And then I can only accept the choice message and then get back to initial state. Okay, so switch back to this. So here's my vending machine. And in my vending machine, as you can see what's happening, I'm creating this actor. To be honest, this is as an example that very, very trivial and not really useful for an actor system because here there's no real concurrency. We're just creating one actor. But it's good to see the idea of transitioning between states, which will become much more useful when we'll see the chat system. Okay, so in this case, we have the vending machine. As you can see, it's created using the initial state, which has been modeled as a method here. And it can only receive the coin message. And when you receive the coin message, it prints, receive the first coin, and it becomes, so it transitions to the other state, wait coins with the amount of the first coin. When it goes to the wait coin state, then we have 2 cases. As you saw, just like in the ping situation, the ping example, we have a counter that gets increased with the amount. So first I'm checking whether I'm going over 100, which if you recall, it's the amount to check to be allowed to pick one item from the machine. All the same for all items for simplicity. And then we actually set the count variable to the actual value, and then we become wait coin with that value, just like we did for the ping, right? We update the variable, and then we recurse, kind of. And in the other cases, so the case where the amount is over, the total amount, it's over 100, then I have enough coins to transition to the next state. So when I transition to the next state, I compute the change that I will release to the user. Let's suppose that you gave like 130, so I have to give you back 30 of change. And then I transition to the event state. And in the event state, I switch over the message with a change that I have to release. I event the product that you pick because that's one of the parameters for choice. And then finally, I release the change, and then I become initial. So I get back to the initial state. Okay? That's pretty much what happens. Yeah, and that is it. So we can run this example, and just to see. Oh yeah, I wanted to show you also coin, but the constructor of coin. But as you can see, I can pick any amount of coin, 50, 40, 30. There are weird coins in these examples, and then I send the message choice with chocolate. Notice here the record. Notice that it has no parameters here. This is a constructor. Records admit constructors, but they do not take parameters. And the reason for that is that the parameter is already here. Parameter and field. So the only thing you can do in the constructor is validating, basically. You can validate your parameters and check and assert constraints. For instance, this case, I'm verifying that the amount is valid for a coin, at least. I mean, a coin that 0 value makes not much sense. With negative value, what does that even mean? And in our case, I decided that the amount cannot go over 100. And that is it. So I can run this example and see what will happen here. As you can see, first we give 50. Then it retransition to the next state. So as you can see, the message, the print have changed to a different kind of message. And then it received the last coin because the amount is over 100. So it's the first it's the different message in the same state. Then it transitions to the last state where it prints vending and gives back the change. A thing that I'm not going to show you, but that you could do, and that will make it a more proper actor system, is that while here we are vending a product by invoking a method synchronously, we could model this by creating new actors and then let them asynchronously do something, like vending the product while the machine enters another state, and things like that. Okay, so that's the idea. And that's how you can model a state machine using an actor. Now, in the next section of the talk, we will actually see how to make this work. We're gonna wait. I spent all of this section to show you the examples and not the actor system. Damn it. Let me see. Yeah, I think we were supposed to see the actor system, right? But I guess, yeah, I guess it's better that we do it after the jump. So, okay. So before the coffee, the thing about closures and classes. So you remember this function and state, closures and classes. So is a functions plus state a closure, or is it a class? So I want to leave this for you to think about while you're having your coffee with this koan. So imagine some, soft music in the background. The venerable master Kusina was walking with his student, Anton. Hoping to prompt the master into discussion, Anton said, "Master, I've heard that objects are a very good thing. Is this true?" Kusina looked pityingly at his student and replied, "Foolish pupil, objects are merely a poor man's closure." Chastised, Anton took his leave from his master and returned to his cell, intent on studying closures. He carefully read the entire Lambda, the ultimate series of papers and its cousins, and implemented a small scheme interpreter with a closure-based object system. He learned much and looked forward to informing his master of his progress. On his next walk with Kusina, Anton attempted to impress his master by saying, "Master, I've diligently studied the matter and now understand that objects are truly a poor man's closures." Kusina responded by hitting Anton with his stick and saying, "When will you learn? Closures are a poor man's object." At that moment, Anton became enlightened. See you in 10 minutes, and we'll see how the actor system is actually implemented and the chat and Loom. Welcome back. Hope you have enjoyed so far, and I have to go a little faster here because I had so much fun in the previous segment that I forgot that I had to show also the actor system. Okay, that's the meatier part of the talk, so I'll try to be fast but not too much. And if I'll have to chop off something, I'll try not to be the most interesting part, at least. So maybe we won't see the chat system in detail, but we will definitely see the actor system because that's the most important part, of course. That's the promise of the talk, after all. All right, so let's start with our actor system. So our friends, the address, the behavior, the effect, we've come to know them and love them, so I won't have to explain them again. So, and of course, if you need, there will be slides online, there is the material of the workshop that we did, and of course, the blog posts. So I'm going to start with the system, the actor system, which I could write like this with a class, and then I have to write a constructor. But as you have learned, I am nasty, and I want to make people a set. So in order just to spare just a couple of lines, I'm going to use a record. And as you've learned, the actor of method is the method that actually creates the actor. Now, as you know, as you see, this is returning an object of type address. So what I'm going to do here is create an instance of this object, which is an interface. So I'm going to create it just here, implementing the tell method. All right, yeah, I don't need to do that like this because I've stopped the tell method. Okay, so this is my tell method. Let's comment it a little bit. It takes a message, which is an object, and that we know, which is that's the signature that we learn, and then we have this MB to which we offer something, and then it calls this a sync method. Okay, so what's MB? MB is the mailbox. MB stands for mailbox. And why did I not write mailbox? Of course, to be shorter and stay in the screen, because we want to be very close to the Scala original implementation, and that's the sole reason for doing that. So I'm going to use a concurrent link queue, and it's a concurrent link queue of objects. I'm going to call it MB, and I'm going to instantiate this, okay? And that is it, all right? Now, the compiler is now happier because because offer is no longer broken, of course. Now we have another issue, though. We have a sync. So what's wrong with a sync? Well, it's just undefined, so let's define a sync. And what is a sync? So you can see here that the signature here is address, but it could be just as well void. I'm just doing address because then we can chain the methods, and in fact, it's just returning this. And that's all it does. So what about a sync? This is already more interesting. The sync method is verifying whether the mailbox is empty. If the mailbox is not empty, then it means that we have received at least one message. And then there's this on guy here, and this on guy here is an atomic integer. This is going to be just a 0 or 1. It could probably be just an atomic Boolean, but it's fine. It could be just like that. And yeah. Okay, So that's what we're doing. So let's comment a little bit about this bit of code. So when I'm receiving a message, so when someone called tell on this address, what's happening in this implementation is that I'm putting the message inside a queue. You remember the mailbox. The mailbox is where actors receive their message. And then at some point they're woken up, look at their queue, and if there is some message inside the queue, they dispatch it to the receive, to the behavior, to the receive method of the behavior, so to the function that actually handles messages. So, so first we offer, then we call this a sync. So what a sync does is it checks whether the mailbox is empty. If it's not empty, then it sets this on value to 1. It sets it to 1, expecting it to be 0. So on means the actor must be, so as you can see in the body, it's scheduling then this actor over the executor service. So what this means is that we are making sure that the actor is not running already, and if it's not, we schedule it over the executor service. So what I've not said so far, we have mentioned executor services, but we haven't really said why we need an executor service. The executor service is the beating heart of our actor system. It's really, the actor system really can be seen as a wrapper for this executor service in a way. It's a convenient way to write a task that gets scheduled over and over again to an executor service, and every time it gets rescheduled, it will handle the message. So now what is happening here is that we're just checking when an address is told a message. So when we send a message, we are putting the message on the queue. We're making sure then that the actor is not already running. If it's already running, we don't need to do anything. But if it's not, we send it to the executor service. And then all we're doing here is some cleanup. So when the execution is terminated, if there is some exception, we reset and we put everything as it was before. So this is complaining about something. It's complaining because this is not, we cannot really submit this, but what we can do here is writing this run method, and then I can just write this, and this should work, okay? So what's happening in the run method? Now I really need to go on a new line. That's also because I blown up all the, the font size to be readable. But let's see what's happening here. And this should answer one of the questions that I've received in break. So what's happening here? This is the actual core of our actor. The other is just not boilerplate, but it's setting up stuff. So what's happening here? We are when the actor actually gets scheduled and the executor service executes the actor. What we're doing here is that we check the on value. And again, we verify that we are actually running, because this is a concurrent program after all. So the value may have changed in the meantime. So if we are still running, then we can check our mailbox. So if our mailbox, so with Paul, and Paul, it's the method that returns immediately without blocking. This is very important. We cannot block in the body of an actor. We cannot block in a runnable. This is a runnable. It's a way to run a runnable, because of course the execute method takes a runnable. So we cannot block, otherwise we will block the execution of that thread. And that means that we will basically we will not release that resource, and we may exhaust the resources, the number of threads that our machine is able to manage. So in the body of an actor, you should never block. Which, if you notice, what's happening here is that we are actually finally invoking the behavior. And the compiler is complaining because we haven't define the behavior field. So let me define the behavior field here. So I now need to remember how that was defined. So behavior field, oh yeah, initial behavior, right. There we go. The initial behavior, or as I called it, the constructor somehow, works like this. So we need a field for the behavior, and behavior, as you saw, may change during the execution of the actor. So, I think I forgot something here. I may have forgotten the constructor itself. Oh no, there it is. Okay, right. So we have the constructor as the argument of our method, and then we refer to it here. So what's happening here is that our initial behavior works like this. The first message it may receive is an address. And that's kind of weird, but we're going to see why that happens. But as soon as it receives an address, which we can send because the behavior always is able to receive objects of any kind, we become the behavior that we get by applying the constructor. I don't want you to think too much about it because that could be complicated. But the idea is that as soon as we initialize the actor, as soon as the actor is ready, we actually assign the behavior that was defined at the beginning. Let me just move back to the ping example. So remember, this was defined in this weird way. So this is the real behavior. This is the real behavior, and this is the constructor. And as you saw, this is an actual constructor. This could be an actual constructor in some cases. So the reason why we want to write it that way, we're going to see it. But first, let's focus on the body here. So we are scheduling our actor for execution, and it has a run method. So it can be scheduled, well, I have defined it this way, so it's a lambda, but it's a runnable now. Okay, so what's happening here? I'm polling for a message, and as I said, this won't block, and this means that because it doesn't block, in some cases it could be null. So let's check for it to not be null. But besides that, let's see what happens here for the behavior. Sorry for the detour. So what's really happening here is that, if you recall, when I invoke a behavior, I'm getting back an effect. And this was the reason why I didn't use a function to define them. Otherwise, you would read apply, and in the one-liner, it's not really clear what's happening. And if you recall, then the effect has a transition method, which take the current behavior and return the next behavior, right? So what I'm going to do here, I want to do this, right? I want to assign the behavior. What's happening here? Right. I want to assign the behavior, the new behavior to the field, so that to the next. So let's see it again. I'm receiving a message. If a message is not null, I'm applying the behavior to the message. So I'm handling that message. Now the behavior may return an effect. It always returns an effect. The effect may be stay, which means it could just return the same behavior, or it could return another behavior. And in fact, the effect takes the current behavior and it returns something. So stay was defined as the identity function because if I'm staying there, I'm literally returning the original behavior. And if not, I'm reassigning it. So that's why it was defined in that, why I used explicit names. Okay. Now this still doesn't work for one reason. It doesn't work because there's a problem. We need to be able to feed back the reference of the actor to the actor itself. And the only way to do this in a thread-safe way is to actually send the actor its own address. Otherwise, there may be race conditions in some cases. So what I'm going to do is I'm going to tell the address that that's its own address. And then I can just return it. And since this is chainable, I can just do it like this. And that's basically all there is to it. So this is our actor system. It's pretty much done. I wanted to spare a few words on the behavior that we have here, which is the initial behavior. As you can see, this is what's happening here down in the last line. I'm telling the address its own address so that it can store it. It can invoke the constructor, the initializer, so that it can be fed back its own address, so that the closure or the object can have a reference to itself. And this is very important because in this particular case, addresses and pointers, references, they are the same. But if we were, for instance, in a distributed case, the address may be just a symbolic representation of a, I don't know, HTTP address, TCP address, whatever. So we need to be able to tell the actor what that is. It cannot use this. And it cannot use this because the behavior may change. It could be a function of any type, and it cannot refer to itself just as simply. So that's something to think about. Anyway, it's not that important that you understand all of this. The most important part really is this. So at its core, the actor is just an abstraction, at least in this implementation, it's just an abstraction over an executor service. I wanted to show you something extra. How much? Yeah, we spent already 15 minutes on this, so I'll go quickly. The reason why this was this and instead of this run, it's because I had used another shortcut that I really wanted to show you because it's silly, but it's another way to impress or scare your friends. So you cannot really, the idea here is that you cannot submit an address to an executor service. And of course, if you do this, colon, run, you're passing a method reference, and it will still work. But you may want to do something like address and runnable together and instantiate them, but you cannot really do that because this is not Scala, and this is not proper syntax. So what we can actually do is create a class. You could create an interface somewhere like here, and let the interface, and let's call it a runnable address, okay? Runnable address, and let it extend both address and runnable. And that will work because now you can say runnable address here. Runnable address, come on, dude. There you go. Okay? This is not the thing that I wanted to show you. The thing that I wanted to show you to be particularly nasty is that, I don't know if you know that, but you can create local interfaces. This is an interface in the body of a method. Ugh, that's horrible. But it can be useful in some cases. You can actually you can also create local classes, local objects, local records, of course. And it's weird, but it works. It's not really important for this because you can actually use a method reference. But in fact, in a blog post, I used this technique because I was following basically the original implementation, and that was kind of the way you could do it. And I really, really didn't realize that you could actually just pass a method reference, and it would have worked anyway. Okay, just so you are convinced, this was my actor.java, which I rewrote from scratch, and I'm going to try to rerun this, and if it actually works, you should do the same. Yes, it does. Please applause. Thank you, thank you, thank you. All right. I'm going to go very quickly on this tiny next segment because it's not that important for comprehending the rest, but I wanted you to see that. So we can actually do a typed version of this. And a typed version of this is really cool because now you can use sealed types to do proper pattern matching with exhaustive matches. And that's really cool. I don't think we have enough time to see that. Maybe I can show that in the chat. I'll see if there is one case there. But basically, this all amounts to doing this. The address becomes now typed. And of course, since the address is now typed, Now it's typed because the message is typed. You see? So now my addresses have a specific type, and it means they can only receive messages of that type. So basically what happens here is that I will no longer need to do a pattern match against default. I don't need to have a default case because I will know that that's the type, for instance, if I use a sealed interface. So if I define my message using a sealed interface, I will know that those are only the type of messages that I can receive, and I no longer need to have a default case. Now, this, of course, will trickle everywhere in my interfaces, because now the receive method must be T, it must receive a message of type T, and then I will have to update effect, and of course behavior now will be a row interface, and I will have to do that everywhere. And of course, we have baked this already for you. That's pretty much the same as the original one, that's the one that we saw. I wanted you to see the untyped version first because I think it's a little simpler. There are some situations where the typed version, there's some trickery there, especially the initializer, the constructor, must be handled in a slightly different way. We're not going to see that today because otherwise we're not going to see the rest of the presentation. Okay, so we're finally there to the actor-based chat. Okay, so that's the third blog post that entitled Write You a Chat, or the second blog post, Write You a Chat. And in the blog post, it's the untyped actor system is being used instead of the typed one. So what's a chat system? So you have a server, and the server, it's a message relay. So when it receives a message from a client, it basically distributes the messages to everyone that's connected at that time. All right? So the idea is that we want to handle each connection as an actor. All right, let's switch to that. Yeah, I'm pretty proud of the example because there's Duffman that send the server, and are you ready? And then Carl and Lenny are happy, but Barney, which is the designated driver, is not happy. I don't know if you get that quote, but... Okay. All right, so the chat system. So this is the Loom chat, but I want you to see first the other type of chat, which is this one. Okay. So I'm going to start with the server because it's simpler. Yeah, this is as you can see, there is a sealed interface. We define the interface called client protocol, and then we have a message that's client connection, a message that's called message, which contains the username of the person, of the client, of the user that sent the message, and then the body of the message, and then line read this is a message that comes from the from the wire. So we will handle the connection using an actor, and this actor will send messages that we will use to communicate with a server. Okay, one thing that I wanted to show you about JBang, specifically about JBang, is that we cannot just source source code. So we can load some source from some files on the file system without having to set up a complicated project. Just have the file lay in there and it will work. We can also use dependencies. So here I'm using Jackson. So what will happen here is that I will receive from the wire a message that's serialized as a JSON, and I will use Jackson to deserialize that. So let's see very quickly how this works. First, let's see this. So a client is very simple. Our client reads from the standard input, and it uses a scanner with its default settings to parse the line. All it will do is basically chunk the line, chunk the standard input. So in is system.in. It will chunk the standard input as soon as it reaches a new line. When it reaches a new line, what it will do, it will create an object message with the username and the actual message, and tell and tell the client actor. So this actually blocks, but it's fine because it's blocking the main thread only here to receive input. So it's good because we want the client to sit there while the users type. Okay, so what it's doing here instead, we are creating an actor that handles the connection. So if you recall, what I said before is that you should never block in the body of an actor. That's bad. So what we did here is to provide a wrapper around java.neo, so not the bare bone socket interface of the JDK. We provided a wrapper for one simple reason. Java Neo was there before Lambdas, and so and before Java 8 and before completable future, and so the API, it's a bit inconvenient to use. So all the wrapper does really is providing with wrapping it with completable futures because it's neater, it's easier to use then. Now, I just want you to see this, and I don't want to go too much into it. What's happening here is that we're invoking this library function that we created. So we open a socket here, and we connect to a host port, which is the default. It's just localhost and then some predefined port that we picked. And we create an actor that is in the client connecting state. So the behavior, the initial behavior is connecting. So it's not ready to receive messages. It's still, initializing. So what we're doing here is invoking this method for the channel, which returns a future. What the future does is that it returns a socket, a proper socket connection, once it's actually ready without blocking. And that's why we wanted to use this. If you use the traditional API, it will totally block your thread, which is not what we want. So when the socket is ready, we will send this in a message to our actor. So our actor is in this state. As soon as it receives the client connection message, it actually performs the proper connection, it prints a message, and then it will transition to another state, which is client ready. In the meantime, it will also create another actor that we're not going to see. Well, we can see that later. Another actor, what this actor does is handling the socket for us. So it's doing some, it is actually receiving, chunking the data that is coming from the socket, which will be a long stream of characters. And as soon as it reaches a new line, because that's the format that we will use, JSON separated by new lines, it will give back to our actor, which is now in the client-ready state, the line read message. So let's see this again, quickly. When we read a message from the standard input, we're going to send the message to our object, to our client actor. When we receive the line read message from the socket, we are going to do something else. So in the case of the message, we want to write to the socket. The socket has been modeled itself as an actor. So we tell the socket another message that it's a built-in, another message with a payload, and the payload has been serialized as JSON. And what it will do, it will just write on the socket the string. As for the line read, when the line read arrives, it's a string which has been chunked by the socket and by the socket actor. And what we're going to do is invoke Jackson, this time not to serialize but to deserialize, and then to print on the screen. Okay, let's see quickly what the socket handler does. Basically, all the socket handler is doing is receiving characters from a buffer, and then it's collecting these characters until it finds a new line. And if it finds a new line, it chunks the message. So basically, it's a sliding window over a buffer of characters, and we're buffering until we find a new line. Because this is encoded through JSON, new lines literal new lines can never appear in the stream because, they can never appear in a message because they will be transformed and escaped. So the only time where we find a literal new line is when we have finished reading one message from the socket. So we can pass it along. Okay, so that's how the client works. Sorry, I'm going so fast. This is probably the most complicated version of it, the most complicated part. Oh, maybe I can also show you something in the client. Yeah, in the client, as you can see, there are 3 messages here. But as you can see, there's no default case because we are handling all of the possible messages that are available. The one reason why there's a yellow squiggly line is only because my editor is telling me that it's a preview feature, but there's no error here because I'm handling all the messages that are possible in the protocol. Now, for the server, again, I cannot go too much into the details of this because we don't have enough time. So yeah, I wanted to go slow, but apparently I went too slow. Okay, so the idea here, it's not that complicated really even here. So we have an actor that receive client connections from the socket. Again, the socket is modeled after Neo, so there's no blocking, all it's good. What the server does is that when a new incoming connection arrives, it means that a new actor, a new client, is connecting to the server. So every time a new client connects, I'm spawning an actor for it. And I'm putting them inside, and I'm handling them through another actor that's called the client manager. The client manager receives all the line reads from the socket handler, which is the same as the client. The cool thing here is that we had one implementation of the thing that chunks messages from the stream of the socket, and we reduced that. And every time we get a line read, we propagate the line read to all the clients that are connected. And as you can see, it's not a lot of code, even the server. Unfortunately, we don't have enough time to see both this and the Loom version, so you will have to take this for, for good. But yeah, as you can see, we're instantiating the same socket handler here, and these are all the messages that we're handling. And as you can see, there's no default case because again, I'm handling all the possible messages here. So let's see this in action. I'm starting the chat server here. I'm starting the chat client here. As you can see, it's saying 444, and I'm connecting through Paul, and I'm connecting someone else, and connecting George. Let's see. All right. And I'm saying hello, and you see that Paul says hello, and this is propagated to everyone, and hello to you, and this is propagated to everybody. All right? Okay. Now, about Loom. The reason why I wanted to get there. Yeah, and as you can see, this is the picture for the line read, right? Okay. As I said, thou shalt not block. So Loom, a couple of words about Loom. I had a few slides because I thought we had more time, and probably I should skip over these. And some people think that green threads are the same as Loom because Java used to have a feature called green threads. This is not really the same thing. If you want to learn more, probably it's better that you just read the article on InfoQ. I think it's by Brian Getz and Ron, maybe. So take a look at that, and we'll explain everything. But the cool thing is that they have more in common with user mode threads in Go or Erlang, which is the reason why it's important and interesting to say something about them. Yeah. Okay. So Project Loom is intended to explore, incubate, and deliver Java VM features and APIs built on top of them for the purpose of supporting easy-to-use, high-throughput, lightweight concurrency, and new programming model on the Java platform. If you were here in the morning, they showed structured concurrency. And the interesting thing about virtual threads is how, in a way, you could see how they relate to the idea of actors, in that you want to reuse them. You don't need to reuse them, but they're lightweight. But we'll see. The virtual threads work this way. They're mounted on top of platform threads. So what's a platform thread? A platform thread is an actual operating system thread, or to be more precise, it's a thin layer, it's a thin wrapper around an operating system thread. The cool thing about Loom is one of the things that they did to make this convenient to use is that they modified the standard library so that it integrated with Loom in such a way that threads yield when there's a blocking operation. And all blocking operation, or at least some of them, they're finished doing them as far as I've understood, but a lot of them, like waiting on a lock, have been rewritten so they do not really lock. They release the lock, and virtual thread will still lock. Well, we'll see that what I mean in a second. Okay, so the cool thing basically is that you will now be able to write imperative code that blocks without actually blocking a platform thread. And because virtual threads are lightweight, you can create as many as you want, which means that you're not going to exhaust the resources of your system apart from memory. So the only limit is your heap memory, and that's it, which is pretty cool. In fact, the cool thing about actors is that you can create many of them because we are reusing threads through the executor, and similarities do not stop there. So I wanted to also give you a reference to this talk that I love, and it's from 2015. It's by Ron Pressler, who's, I think, the architect. I don't know if that's the right title, but he has been leading, anyway, the Loom effort. And at this point in time, he wasn't working for Oracle yet, but he definitely had the idea of this idea in mind. This is a talk that really explains what's the power of virtual threads in JDK. You can literally write blocking code as you would write blocking code in a simple way, and it will actually be handled in a way that it's not harmful for your system. So in this talk, it explains why it's explained why, in a way, reactive systems written in a functional way are kind of harder to follow, and why people may prefer writing in an imperative way. May prefer. So in this case, through virtual threads, you can actually block. You should block, in fact. The cool thing is that not only you can block, but when you do a blocking operation, that's the point where the runtimes let you swaps your threads, your virtual threads, for another thread. So that's actually something that you're supposed to do because you will get a higher throughput, which is kind of mind-blowing, if you will. So let's switch to the Loom chat now. Yeah. So there are two interesting things about the Loom chat. One of them is the chat itself. The other, it's the runtime. So the Loom chat itself, well, it does block in some places, especially in the server. It's actually using some APIs that are blocking, but I wanted to just show you the runtime, because even the runtime is pretty interesting, and it should, explain the situation. We'll start from here, and then we'll see if we can actually have time for the chat itself. Okay, let's see what's happening here. We still during Actora, we still instantiate our runnable address that we saw previously. And then we submit to the executor service here. Now, let's see what the runnable address is doing. We still have our initial or constructor. And this is our initial behavior. And now let's see what's happening here. What tel does is still does an offer over the queue. and then it returns itself, and that's all fine. As you can see, there's no longer an atomic integer here. And then you may notice two things. The first thing, this is a linked blocking queue. This is a blocking queue. This is supposed to block. This is actually blocks when you take. So what is happening in our run, right? If you recall how our run was written before, well, let's take a look at it. Our run returned immediately, basically. It even did a poll instead of a take, because this is an operation that returns immediately. And then it applies the behavior, and the cost of the operation of executing this is only the cost of executing that function, and all that is. You're not supposed to block here. We are not blocking here, and we're not blocking even in async because it's invoked here. Now let's see the other version. This is still the same version. There we go. There's no async. There's only run. We are in the body of the run. We are not submitting to the executor service, because we submitted to the executor service in the actor of here. The body of the run, it's a while true. So it's something that's looping forever. And we are taking from the mailbox, which is a blocking mailbox, which means that we'll block the while true. And actually here we want to block the while true. Otherwise the CPU will spin to 100% because it's a while true. Okay? So we want to do a blocking operation here. But again, if we do a blocking operation here, we're gonna block a platform thread, and bad things will happen. We'll see right now what will happen, and let's see if everything works the way it should. Okay, so I'm gonna switch to the other chat, the Loom chat. Yeah, before I switch, I'm gonna create a fixed thread pools of 5 threads. The reason why I'm creating a fixed thread pool of 5 threads is for demo purposes, and in order to show you that something bad will happen without creating hundreds of clients, otherwise it won't work. So for the way we have model clients in the server, we need 2 actors. And so one of them is handling the socket connection and the other is handling the actual messages. So if we create a fixed thread pool and we create 2 client connections, then we will max out the number of possible connections, because one is for the server, one is for the one client socket, the other is for handling message, and the other 2 are for another client. If we connect a 3rd client, let's see what happens. Now the problem is, let's see if this actually works, because otherwise this is going to be a very loosey demo. All right, so I'm going to start the server. And the output is pretty much the same as before. I'm going to create a client, a client, a user. I'm going to create Paul. And I need another one, yeah. Yeah, and I'm going to call him, well, let's call him Ringo. Okay, so let's try. Let's see what happens if George writes something. Hello. Yeah. Hi. Yeah. You see, there's no echo, there's no propagation of messages because I maxed out all the connections. And I think we should still see the other two chat with each other, but unfortunately the other one is on the side. Who needs him? He's just playing the drums. And so this is something that I wanted to show you too. If we take a look at this, I hope you can see this. Yeah, it's a bit tiny, but yeah, you should be able to see. This is our thread pool, and you can see that, confusingly enough, at least for me, red means that the thread is parked, and green means that it's running. So red means that it's good, and green means that it's bad in this case, because green means that they're spinning to do nothing because they're awaiting, but they cannot be released. So that's we're basically in a deadlock situation. Okay, but let's now see what happens if I instead switch to our, so let's kill this. And let's switch back to my editor. And what I'm going to do here is creating a very simple, this executor service. This executor service, all it will do is creating one virtual thread per task. So it may create infinite. So let's retry again. So applause. No, but the important thing that I need to show you before is that you will now see that all the threads are parked, which means that they're doing what they're supposed to do. They're doing nothing because nothing is happening. So everything is cool, everything is good. I also wanted to show you how this is really equivalent to literally spawning a new virtual thread every single time, because that's what actually the executor service is actually doing. So I mean, even if try this again, which is at this point very, very boring, I understand it, you will see exactly the same result, because that's what's happening really under the hood. So for now, I'm going to be less fancy just to show you that it actually works. So you see, it's literally doing the same thing. Okay. So yeah, I think it's a good time here to stop. So what I wanted to tell you at the end is that there's a bunch of interesting sessions for the whole conference, but of course I'm going to promote my friend and colleague Mario Fusco, who's going to do an interesting session on how to implement a game of life using Loom. And doing some interesting considerations about performance and how you write code, what's the proper way, what's the idiomatic way to write code using proper Loom. So, Game of Loom. And this will be on Thursday, so save the date. If you want to know more, of course, there's the blog post. If you want to try this yourself, there's basically all of the code on this repository. This is the address. If you want to follow me on Twitter and shout things at me, I talk about Java and WebAssembly and other crap. So that is all, and thank you for staying with me all this time. Hope you enjoy this. And if you have any questions, I'll be around.